Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional unceded lands of the Lekwungen peoples. Welcome back to Stories from Space. I am your host, Matt Williams. Today, I wanted to get into the subject of extrasolar planet research and the search for life in our universe, otherwise known as astrobiology. This field has become increasingly relevant in recent years. With over 5,000 exoplanets now on record, scientists are beginning to make a transition away from the whole discovery process and are getting into exoplanet characterization. And what that means is we're beginning to move from indirect methods of confirming whether or not exoplanets exist and whether or not they could be habitable into more direct methods. In the coming years, these studies are going to benefit greatly from telescopes like James Webb and ground-based telescopes that are going to have larger mirrors and more sophisticated optics and instruments. So this raises the question, how exactly do we determine planetary habitability? How do we determine in the future if, in fact, there's any indications of life on a planet? It's one thing to say a planet is potentially habitable based on how it orbits the sun. It's another thing entirely to say that, in fact, we have detected signs of life there. And when referring to the possibility of life, scientists are basically looking for what is known as biosignatures, which is to say the chemical indications of life or processes that we associate with life. Now, before we get into what scientists consider to be examples of biosignatures, there is the question of what are the current methods, which are still largely indirect, for confirming the existence of planets around other stars. Now, as we explored in a previous episode, which was dedicated to exoplanet research, the study of exoplanets has exploded in recent years. In 1992, the very first confirmation of a planet beyond the solar system happened in 1992. But within the last decade and a half, that number has exceeded 5,000. Now, the reason for this had to do largely with the development of space telescopes, in particular the Kepler Space Telescope, as well as Hubble and the Transiting Exoplanet Survey Satellite, or TESS. And the process of discovery, it hasn't slowed down one bit since Kepler's retirement. In fact, it is now getting into overdrive. As I said, it's officially making the transition away from simply spotting planets in distant solar systems, and it's gotten into characterizing them, which is to say determining their characteristics of their atmosphere and surface and what conditions are actually like on those planets. And as we also explored in this previous episode, the most popular method for detecting exoplanets to date have been the transit method, where you are monitoring distant suns for periodic dips in brightness, which could indicate the presence of planets passing in front of the star, or the radial velocity method, where you monitor distant stars for signs of wobble in their orbit, which indicate that there are massive objects pulling on that star, in other words, a system of planets. Now, these two methods are both very good at determining both the presence of planets, and in combination, they're very good at determining the size of a planet, its orbital period, its distance from its star, and just how massive it is. And from those methods and a handful of others, scientists have been able to say that, well, this star orbits its sun at the following distance. It is tidally locked, meaning that it has one side facing the sun at all times, or it's far enough away that it's able to make full rotations, and it would be receiving roughly this much radiation from its sun, which, if in fact there is an atmosphere and possibly a magnetic field, would indicate that, yes, water could remain in a stable form, liquid form, on its surface, thus making it potentially habitable. And yes, this region in which a planet could orbit and maintain liquid water on its surface is known as the circumsolar habitable zone, or the habitable zone for short, or the Goldilocks zone, where conditions are just right. But with telescopes like the James Webb and the upcoming Nancy Grace Roman Space Telescope, and ground-based observatories like the Extremely Large Telescope, the Giant Magellan Telescope, the 30-meter telescope. Now, in the case of the ground-based telescopes, they're going to have these 30-meter wide mirrors, plus adaptive optics and coronagraphs and filters and spectrometers. In the case of the space telescopes, they will also have coronagraphs and spectrometers, but will not need giant mirrors or adaptive optics because they operate in space. And that will allow them to be able to see the faint traces of light, which are reflected from exoplanet atmospheres or from their surfaces as they orbit their parent star. And this is where the coronagraphs come in. They will block out the interference, the light interference from the star itself. Using the advanced spectrometers, they're able to see the telltale indications of chemical signatures. Basically, the way light is absorbed by an atmosphere and radiated is directly attributable to the presence of certain chemical elements. So when that information is available, astrobiologists will be looking for what they see as the telltale signs of life. And using Earth as a template, right now, astrobiologists are looking for things like hydrogen and oxygen, which are the chemical indicators of water. And this is in keeping with the whole follow the water method, which is to say that water is an indication of life because, as we know from Earth, it is the one solvent in which life can flourish and emerge, and it's also an element that all life depends upon. By the same token, they're also looking for methane and ammonia, which are also associated with organic processes. In the case of ammonia, it is a nitrogen waste that's produced by aquatic organisms largely, and it's also a major contributor to plant growth. Methane gas, meanwhile, is emitted as a result of organic decay. When organic matter or living creatures die, it is a natural byproduct. It's produced by several animals, their digestion cycle, such as cows. And it's also associated with, on Earth, landfills. So the presence of methane in the atmosphere would indicate that a lot of biological processes are going on there. In addition, there's carbon dioxide and oxygen, both of which are very much associated with organic life here on Earth. CO2 was an abundant chemical element in Earth's primordial atmosphere, and that slowly began to decrease as photosynthetic organisms emerged, beginning about 4 billion years ago, like cyanobacteria, and they relied on photosynthesis in order to process CO2, and they emitted oxygen gas as a waste product, until the Great Oxidation Event, which occurred roughly 2.5 billion years ago. And at this point, more complex life forms, like terrestrial organisms, began to emerge that were dependent on oxygen. And this has continued to this day, where all complex terrestrial life forms and aquatic life forms are dependent upon oxygen. And this includes oxygen that is dissolved in water, and also oxygen gas that's floating around in the atmosphere. And conversely, we emit carbon dioxide as a waste product. So CO2 and oxygen gas are considered very important biosignatures, and as a greenhouse gas, CO2 is also considered a very important climate stabilizer. So it helps ensure consistent, or at least relatively consistent temperatures over time, in spite of the fact that the planet may experience changes in its axial tilt or in its orbit that would cause temperatures to change on surface. And there's also volcanic hydrogen. It's not so much the hydrogen itself, but the presence of volcanic activity. Hydrogen can also be a greenhouse gas and lead to warmer temperatures. But volcanic activity and plate tectonics are considered vital to the evolution of life here on Earth. Certainly life as we know it has in part been dependent upon the presence of tectonic plates and their movement across the planet, which is constantly leading to surface renewal. It's leading to volcanic eruptions. It's leading to the enrichment of soils around volcanoes, and fissures on the ocean floor and hydrothermal vents, which are also vital to life and are considered to be where life emerged first on planet Earth. And another method that is going to become very, very invaluable in coming years consists of looking for signs of photosynthesis on a planet. Because if you can examine light reflected from the surface of a planet through spectrometers in considerable detail, you can actually see detections of green vegetation and purple vegetation and the photosynthesis that drives them. Now, this is based on decades worth of Earth observation, and it relies on what's known as the vegetation red edge. And this refers to how green plants on our planet will absorb red and yellow light while reflecting green light. This gives them their appearance. They also emit infrared energy at the same time. And this is something you can see from orbit simply by looking at the proper spectrums of light, looking for green wavelengths and infrared wavelengths. And the same is true of retinol-based photosynthesis, which is what leads to purple plants and also photosynthetic bacteria that are also colored purple. Retinol is what gives them the color, and they too absorb light in specific wavelengths. In this type of photosynthesis, light is absorbed in the yellow and green part of the spectrum and is then radiated at the purple end of the spectrum along with infrared heat. So, by looking for these specific signatures of light on the surface of a planet, scientists would be able to map vegetation on exoplanets the same way they do on Earth. And this would not only confirm the existence of life on other planets, but it would show that complex life has been evolving there, and it might also give rise to the detection of other life forms. Now, you may be wondering at this point, what's the catch, or what are the limitations here? And you may have noticed that throughout all the biosignatures that I mentioned and how we look for them, they all come back to one simple thing. These are all based on life as we know it, which is to say, life here on Earth. And this has always been the paradigm and or paradox of astrobiology, and also certainly in the search for extraterrestrial intelligence. It's that we only know of one planet in the entire universe right now where life is supported and where life is able to thrive and replenish itself, and that's Earth. And its particular life forms, and that includes us, these are the only real exemplars we have. So using Earth and the evolution of life on it, this is what informs the search for life out there in the cosmos. And of course, critics would say that, well, this is only life as we know it. This is a narrow focus. We're confined to looking for water. We're confined to looking for oxygen and nitrogen and a few other chemical substances and evidence of photosynthesis. How do we know that life won't take other forms? That it won't be entirely exotic compared to life here on Earth? And therein lies the paradox. We don't know that at all. Which is why we're confined to looking for life as we know it, because we really don't know of any other chemical basis or chemical regimens under which life could exist. We have theories, and we certainly mean to test those theories in the coming years. For starters, there is the popular notion that life could be silicon-based. And this is something that's been around for decades. It's been explored both as a matter of scientific inquiry and theory, and it's also brought up repeatedly in science fiction for that exact reason. Scientists have considered the possibility that life in our universe might use silicon as a base element rather than, in our case here on Earth, carbon. And this is not without merit because, as we know, silicon is the 8th most common element in the universe, and we see it everywhere. It's the basis of silicate minerals, which make up the Earth's crust and all rocky planets, and it's also found in great concentrations throughout the asteroid belt. It is a major component also in the gas giants, where it is speculated that even gas giants have a rocky interior and a metallic core. So we know it's in abundance everywhere. So the idea that it could be the chemical basis for life has been explored. And looking at the solar system, again, Saturn's largest moon, Titan, scientists have been very preoccupied with its environment because, in spite of being very, very cold, the moon has a very dense nitrogen atmosphere. It is rich with organic molecules like methane. In fact, Titan has a methane cycle which is pretty much identical to Earth's water cycle. Methane is a solvent like water, And on Titan, it exists in liquid form, in the forms of great methane lakes across the surface. It exists in its gaseous form in the atmosphere, and it experiences precipitation and rains down onto the surface there. And not only that, but scientists have noted, thanks to the Cassini-Huygens mission, that the surface of Titan is a very, very rich prebiotic environment with all kinds of organic molecules and organic chemistry going on. And this has led to speculation that maybe, just maybe, there could even be life down there. And it's speculated that this life would most likely be simple in nature. It would be single or multi-celled organisms. They may be found in the methane lakes, and that this represents a methanogenic life cycle, which would be similar to life here on Earth in that all the life forms there on Titan or in a methanogenic atmosphere depend upon these organic molecules to survive, and that they conduct organic processes the same way we do. And it's even been speculated as to what the byproducts of this cycle would look like, what types of compounds the living life forms would take in and what they would emit as waste products. What's more, there's a great deal of scientific speculation about the possibility of life inside icy moons like Europa and Ganymede, Callisto, again Titan and Enceladus. Basically, all the major moons in the outer solar system that have not only icy surfaces, but they're also known to have various organic molecules in them, such as ammonia and methane, and that due to tidal fluxing, gravitational interaction with their gas giant, that causes their interiors, which are believed to be composed of rock and metallic cores, this causes them to bend, twist, and flex and release energy in the process. So essentially, they're geologically active in their interior. And this could lead to hydrothermal vents, much like Earth has on its own ocean floors. And so, beneath the icy crust, there would not only be a liquid water ocean. Temperatures would be warm enough to maintain liquid water, but there would also be hydrothermal activity. So all the chemical elements needed for life and heat energy would be blasting out of these fissures at the core mantle boundary, and life could begin there too, much as it's been theorized to have began on Earth. So this is all very, very interesting information there, of course, but it remains speculative and it needs to be investigated further. And that's something we can look forward to because, in fact, in the coming years, NASA and the European Space Agency are both sending robotic missions to the Jupiter system to explore Europa and Ganymede. And this includes the ESA's Jupiter Icy Moons Explorer, or JUICE, and the Europa Clipper mission. And these missions will observe the surfaces of both Ganymede and Europa for plume activity and to look for signs of organic molecules that are being ejected from these water plumes and placed on the surface. And if these missions are successful, there are proposals for a follow-up mission with a Europa lander, which would set down on the surface and examine plume activity and the contents of the ice sheet, again looking for telltale indications of organic processes and life beneath. And there's even proposals for a Europa submarine, which would basically melt its way or drill its way through the ice and start exploring the interior ocean and, again, looking for any evidence that there's life swimming around down there. NASA also has plans to send the Dragonfly mission to Titan, which would depart in later this decade and arrive by the 2030s, and this mission is a quadcopter, a nuclear-powered quadcopter, which would be able to fly around the atmosphere, land on the surface, and obtain samples and do detailed analysis of Titan's probiotic organic environment. And if there is in fact any life there, it would hopefully find indications of it. And there's also plans to send another mission to Enceladus to build on what Cassini had done there. Cassini was responsible for examining the water plumes that come out of Enceladus's southern polar region. And so a follow-up mission is planned where this mission would either fly through the plumes or fly past them repeatedly and attempt to obtain samples and see just what's coming out from deep within that moon. And the results here would not only be absolutely groundbreaking or earth-shattering, they would not only provide the first evidence ever of life beyond Earth, but they would have significant implications for astrobiology that is looking for life beyond the solar system. If in fact we find life within the solar system that does not rely on the same types of chemicals or cycles that life here on Earth does, then we'll absolutely be applying those to the search for life in the universe at large. And this all highlights exactly how our search for life in the universe there. It's complicated by the fact that we really only can look for life as we know it, and under the conditions that we know for a fact life can survive, and for the kind of processes that we know for a fact life relies on in order to take in nutrients, take in energy, and what kind of waste products it creates. So again, this is the complicating factor. We can't look for life that we haven't found yet, or life that we don't recognize yet, because we wouldn't know what to look for. But we are very close, right now, to a point where we can scan thousands of worlds for indications of life that we would recognize. And as the process of discovery and observation goes on, here at home, and also in the universe at large, our frame of reference is likely to expand. It's likely to take into account all kinds of activity that we see out there that can only be explained by the presence of life. And it's very exciting to know that this is something that is really not far away. The ability to examine extrasolar planets directly and to see exactly what's in its atmosphere or what could be happening on its surface. The ability to explore distant exotic environments like icy moons and methane lakes. That's all something that's within our grasp and will be happening in the coming decades. So we can say with high confidence that if there is life out there to be found, we're going to find it sooner or later. And the odds, they're only going to get better. Now, all of this, the search for biosignatures, concerns how we are looking for life in general in the universe. Next time, we'll discuss how scientists look for signs of intelligent life, known by its acronym SETI, the Search for Extraterrestrial Intelligence. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.